Hi, my name is Marek, and I will be telling you about our work on multidirectional associative optimization of function-specific word representations. This is joint work that we did together with Daniela Gerz, Vulić, and Korhonen from Cambridge, myself from Imperial, and Roy Reichart from Technion. In regular word embeddings, we learn one vector for each word type. These are then optimized using the distribution hypothesis in such a way that vectors for similar words will be close together in the vector space. In this work, we extend this idea and learn a separate embedding for each functional word. For example, in a subject-verb-object relation, the words can take one of three possible roles, either a subject, verb, or an object. And if a particular word can appear both as a subject and an object, then we learn separate embeddings for each of these roles. We can then optimize these embeddings in such a way that vectors for plausible word combinations will be close together in the vector space. On the left of this slide, you can see some examples of how this works for the SVO case. We have the verb eat, and around it we have the plausible subjects of eat, such as chicken and cat, along with plausible objects of eat, chicken and food. In this case, chicken can occur both as a subject and an object of eat, but cat is normally only the subject of eat. On a higher level, what we want to do is model mutual associations between n groups of words where each group represents a particular role. For example, in the SVO case, the number of groups is 3. Every group has a separate embedding matrix and a separate vocabulary, but these vocabularies can partially overlap. As we saw before, the word chicken can be both in the subject group and the object group. We then want to be able to pick function-specific embeddings from each of these groups and score the plausibility of these combinations. For example, this would allow us to find out what is the plausibility of cat eat fish, or what is the plausibility of study physics. So how do we actually optimize these embeddings? We can use an idea very similar to skipgram optimization. Skipgram essentially uses two groups of embeddings, the target embedding and the context embedding. And we extend this idea to a more general case with an arbitrary number of word groups. Our model takes n groups of words as input and creates a subnetwork for each possible group-to-group connection. Then for one particular subnetwork between groups A and B, we use the word vector from group A to predict the word in group B. For that, we use a simple linear layer with a bias vector and a sigmoid activation. The capital B in this equation is the embedding matrix for all the words in group B. We then optimize the embeddings on both sides using cross-entropy, so the model learns to predict which words in which roles occur together. There are a few more important properties that we integrate into our model. The first of these is the joint loss. We take the losses from each of the individual subnetworks and we add them together to get the final overall loss. So the final model is optimized with a single synchronous backward pass over all the subnetworks. Second, we use shared parameters. Each group has a separate embedding matrix, but these are shared between all the subnetworks. For example, the verbs have their own embedding matrix, but these same embeddings are used for both the verb object and the verb subject subnetworks. And finally, we do this in a multi-directional way. For every subnetwork from group A to group B, we also optimize the parameters from group B to group A in a symmetric way. Now, why do we want to do this in multiple directions? While skipgram optimizes only in one direction, we found that it is beneficial to optimize the embeddings in both directions at the same time. Otherwise, we need to explicitly choose which direction we want to use, and this can make an important difference. Here we have a small example in the slide about predicting the grammatical genders of German nouns. If we train our model to predict the gender based on the noun, we get a very nice separation between clusters because each noun has only one gender. However, if we try to optimize in the opposite direction, we now lose this nice structure because each gender can map to many different nouns. In practice, choosing the correct direction can be very difficult because instead of n to 1 or 1 to n mappings, we are usually dealing with n to m mappings, and it's increasingly unclear which direction is better to use. Instead, we found that by optimizing in both directions at the same time, we managed to retain the nice class separation without having to determine which is the best direction to use. The idea of function-specific representations is very general, and we can apply it to many different structures. But in this case, we're focusing on the subject-verb-object relation. That means we start off with 3 different groups of words and 3 embedding matrices, one for each of these groups. And we also have 6 subnetworks because there are 6 possible directed connections between these 3 groups. We train the model using known subject-verb-object tuples that we collect from parsed versions of UKWAC and the BNC. And then during optimization, we minimize the summed loss over all 6 different subnetworks in all possible directions. Here you can see some example nearest neighbors from the optimized model. Each of the groups has separate embeddings, but because of the way we learn them, they are still in the same space. So we can find the nearest neighbors within a group. For example, if you look at the verb eat, then it is similar to words drink, consume, and smoke. But we can also find neighbors across groups. For example, in the bottom part of this slide, you can see that food as an object and cat and dog as subjects are also very close to the verb eat in that space. We evaluated this model on several different tasks, and the first one we'll look at is the task of pseudo-disambiguation, where the goal is to identify which tuples are correct and which ones have been randomly corrupted. We can do this with different number of roles, and we experimented with up to 4 different types by adding the indirect object also to the subject-verb-object tuple. In all settings, from 2 to 4 different types, this model gets very good results and manages to outperform previous work. Next, we looked at the task of scoring event similarity. In this case, the model gets 2 SVO tuples as input and needs to estimate how semantically similar they are. For evaluation, we measure how well the predicted scores correlate with manual human judgments. So for example, people run company and people operate company have been rated as being very similar by human annotators. And in contrast, river meets sea and river satisfies sea has been rated quite dissimilar by the annotators. We experimented with several different methods for composing the word embeddings into event representations, and we found that the choice of this composition does make a difference in performance. Overall, the function-specific word representations achieved new state-of-the-art results on 2 different event similarity datasets. Finally, we also evaluated the model on 2 datasets for selectional preference. Here, the task is to estimate how likely is it for a subject to appear in a particular context compared to human annotation. On one of the datasets, the method performs similarly to the previous state-of-the-art methods. And on the second selectional preference dataset, the function-specific word embeddings give a consistent improvement over the previously published results. We also ran some ablation experiments to actually check that the properties of synchronous training and parameter sharing were indeed useful for this model. Here you can see the results for all 4 possible combinations. And for all datasets, we found that the best configuration uses both the joint loss and the shared parameters. To conclude, we propose function-specific word embeddings that provide state-of-the-art representations for multi-word structures and events. We found that optimizing the embeddings with synchronous updates and shared parameters gave the best overall performance. And in the future, it would be very interesting to extend this embedding method by combining it with context-specific word representations, such as Bert or Elmo, in order to get the benefits of both approaches. Thank you for listening. If you have any questions, we will be answering them at the ACL Q&A sessions. And of course, if you are watching this after ACL, then feel free to contact us over email. Thank you.